The title of this project is Early Detection of Implant Loosening to Prevent Total Implant Failure. This project is the coordinated efforts of Rowan University students and faculty with an affiliated orthopedic surgeon from Rothman Institute. Historically, 10% of hip implants will fail within 10 years of being implanted. Of that, 75% of these failures are due to aseptic loosening, which is the micromotion that occurs at the interface between the implant and the bone. After failure, a painful and invasive corrective surgery is required, costing patients approximately $50,000, not including the routine x-rays, hospital stays, physical therapy, and other fees associated with this corrective surgery. Currently, there is no way on the market of detecting the loosening of an implant before total implant failure. The development of a software for detecting early loosening will allow for less invasive treatments like pharmaceutical methods or lifestyle accommodations to be applied prior to implant failure and thus extending the implant lifespan. From this information, we identified a need statement. There's a need to precisely locate a joint implant in the bone and determine its degree of loosening in arthroplasty patients to prevent total implant failure. After working with clinicians, we developed a few design criteria to address this need. Highlights include low cost, accessible diagnostic, and detection of 1 mm translation and 2 to 3 degree rotation. Our solution takes a two-step approach. The first step is the implementation of a secondary reference implant. The second step involves imaging analysis and diagnostics. The reference implant will be implanted at the time of surgery, ideally using CAN, which is a navigation technique, or will be placed near the incision point. The reference implant will be placed in the femur and not attached to the primary joint implant. The next step of our solution is the analysis of the x-rays taken using computer software. With the software, a doctor can look at the x-ray taken right after surgery and compare it with any x-ray taken any time afterwards. To test the validity of our concept, a CAD file of the implant was placed into Autodesk Inventor, then the reference implant and fiducial marker were added to the file. The implant was then translated at 0.5 millimeter intervals, and screenshots were taken at each interval to simulate an x-ray. The same was done with rotation, rotating in 1 degree increments from 0 to 20 degrees with screenshots taken at each rotation. These screenshots were analyzed to see if the same translations and rotations could be found by image day. Next, we tried having the software test for rotation and translation on the same image, but for simplification in this video, I'm only showing testing for rotation, this image day overlay. Doing a random image just to show you the process of how all the work is done in image day, but as you can see, this process is still completed manually by members of the team, and automation will be the future of this project. In the future, we must finish verifying the surgical standards for the secondary reference implant. To shorten the analysis time, we are looking to automate the process that was previously performed in image day. Finally, we will also develop a user manual that will aid professionals in learning the software. Thank you for your time and consideration.